So what I wanted to present now basically was the openCARP GUI that we have been developing in collaboration with openCARP team. And the main goal behind this solution was to approach openCARP to users which don't have a background in computer science, or doctors that want to run their own simulations to perform experiments, and of course they don't have the time or the skills to install in a computer openCARP, which is a pretty big package. So the idea now is to show you how to make it work. You have the installation instructions in the web page, and because it's all done inside a Docker, it's pretty simple to basically download and to install it. I have it installed here in my computer. So once you have basically downloaded and you have started, you only have to basically do Docker compose start. And you will see every time you want to use CARP with the GUI, you just need to start it. And it will start a few modules, namely a database, the application, Paravi Web for visualizing results in 3D, a web server, and openCARP itself. So as you see in my screen, everything is starting. And when it's starting, you can start using the tools. So now everything it's running. You only have to go to your web browser. And then because everything is running in localhost, you just have to type here the direction localhost examples, and then you will connect to the server. If I write it properly. Yeah, so you will see this openCARP examples page, in which there is the tool that we've been developing with all the examples. From here, right now, what is available are the examples that we have opened for this workshop. But the idea is to be able to have more examples, and that you can write your own examples depending on the experiments that you want to do, or that in your lab people usually needs to perform, maybe routinely, that you don't need to code all. So that's gonna make your life a little bit easier. Let's see one of them working. You have here, for instance, single cells, and I think later on you are going to be playing with this for a while in small groups. So we are going to see the basic bench here, for instance. These basic bench correspond to one of the examples that it's already coded, which is modeling electrophysiology at cellular level, in which we are going to stimulate a myocyte with a bicycle cycle lens, and we are going to perform a simulation in 0D. Okay. Maybe if you want to do a simulation in which you have developed your own model, you can try here to analyze the output. In this simulation, we have loaded only the parameters that can be tuned. As we were discussing in previous conversation, openCARP has a lot of input parameters, and maybe some of them you don't need to input because they are not interested for a simulation. So here on the left, you have only the parameters that you can touch. For instance, ionic model, which is temperature. You can add some parameters to modify the conductance, for instance, of different channels, the duration of the simulation, which basically now is 500 milliseconds, the basic cycle length, and some other parameters that you can load here, and some output parameters, and the name of the experiment. So if everything is good for you, you can just press run here. What is happening here in this side is the terminal, it's running. So now in my computer simulation, it's running with openCARP. It's being sent to openCARP. openCARP is performing the simulation for 500 milliseconds. And this is what you will see if you run everything in your terminal using a command line, okay? Then when the simulation is done, you will see here these two buttons, plot data and visualize, in which depending on the type of output, you can see the results. Because we are running a 0D simulations, we can see only the plots of at cellular level of the different compartments and this kind of information that now we are going to review. The system automatically, after the simulation is performed, does all the conversions, so the data can be visualized easily. Now, because my computer probably is doing things like sharing the screen, I see that this is taking some time. Usually it's pretty fast, but now it seems my processor it's a little bit busy with the video, but in general, it goes pretty fast. So now we are going to see here all the plots. The plots that are going to appear here, you can visualize, you can play with them. Okay, you have all of them here. You can remove this panel from the left. Visualize all the outputs at cellular level for the 500 milliseconds that we plan for the simulations. And if you run a little bit down, you can see here, for instance, the transmembrane potential, okay, the typical curve that we all know here for 500 milliseconds. And you can either download it, or you can store it here for later, or do whatever you want. These examples are meant to be done and to overlap each other, but you might be interested in getting this information out of the Docker, okay? Because all the things that we are running here are inside a, let's call it, virtual machine where everything is being run on top of your computer. So you can always enter the Docker and get the data because you want to visualize it in MATLAB or in whatever other system you want. And for instance, for that, you can come here, basically. You can execute a command, basically, to go to the openCARP Docker, and then just enter in the openCARP Docker. You will be inside the virtual machine. So right now, I'm inside the Docker that is running openCARP, and here there are some folders, as you have seen in the hub, where you have experiments, and you have here some experiments that I've already run at tissue level, and there is another called tutorials, where if you enter, you can see also some simulations that I performed. If we go to this simulation, that's the one that we have been running right now, you see the basic bench, and inside the basic bench, you have the outputs. So here you have, for instance, these files called JSON files are the output with all the plots that we have been seeing. You can always copy them into your computer to visualize with whatever system you want. So, or you can run several simulations, and the different simulations will have underscore 0, 1, 2, 3. You can get any of them at any times. Okay, so you can visualize, or you can basically take it from here. In addition to this, you also have here the option to see the help of the case with all the information that is basically pulled from the web server with all the data, all the input parameters, and some explanation of the experiments that you are doing right now. And just to finish, the idea was to see also another experiment which is not 0D. So you can see 0D, a 3D example. I'm going to move to tissue level. Here we have also many experiments. I'm going to go to the first one, the basic usage here. This is a simulation in a slab of tissue. I'm going to increase here the strength so everything runs smoothly. And I'm going to run a simulation of 20 milliseconds in which we are going to stimulate a slab of tissue. And then we are going to visualize the output in 3D in a system called Visualize, which is basically a version of ParaView that can be used through a web page like the one we have here. We convert all the output to N-side format using the mesh tool. So when the simulation is finished, we convert everything. And then you see that this visualize button appears in white color. So if you press, it opens another tab here, and it starts to load ParaView Web, it's called. This ParaView Web, it's going to open the simulation that we've done. But if you run several simulations, you can always see the simulation that you have performed previously. So you see here the experiment _1, because I was playing before, so probably number 0 already exists. This is a slab of tissue. As you can see, you can play with it here in the screen. You see that it's a 3D model, and this probably needs for you to be familiar with ParaView because it's pretty similar, but it's not very difficult to use. It doesn't have all the power of ParaView because it's a small version for the web, but the main things are already included. So we can, for instance, here change the color map to something that it's nicer for us, and then we can here adapt the scale, basically because we want to scale it to the transmembrane potential range, which is here between -86 to 39, just pressing this automatic button that calculates it for you. And then, as you can see here upright, we are in frame 1 out of 201, and you can play and you can visualize the result of the simulation using the web browser. Again, I am playing and I am broadcasting this using my share screen, so it's not going very fast, as you can see, but if you are running your computer, this goes pretty fast, and you can see, at least you can do a simulation, see the output, see if you like it, go back again, do another simulations, open as many tabs as you want if you are running several simulations, and compare them visually or to check that everything is going fine. If you have run simulations previously, you can always come here and you will see these folders, which are inside the Docker, where you have simulations that you have already run, where you have the experiment 0, experiment 1, are previous simulations that I've run. If you have a configuration that you like after analyzing a little bit the data, you can always come here and save the state. So after saving the state, you can also open a simulation and go back exactly to the point where you were before. Okay. Also, you have filters that you can use here. For instance, a clipping plane. If you want to see something inside the 3D model, you can perform a clip that is going to cut this model. You have to provide the coordinates where the cut is going to be performed. So it's not interactive, but for instance, here I'm going to cut right in the middle. So you can see here the cut. And well, this is something, a tool that you can play with. You don't need to install any software in your computer, and you can also give access to other people through a web browser to your system. So you can let other people, students, to access this software very easily.